Hi everyone, thank you for coming. Um, Looks like it's a minute past 10, so we can go ahead and get started. If you have the worksheet for the ion concentration and neural functioning, please pull that out. So last week we looked at circulation, and this week we're going to be looking at the nervous system. So before we really knew anything about the nervous system, a lot of the pioneering studies were done on squid's giant axon, which is why we have a picture of a squid here. And it's saying that their movement, like they contract water using the muscles of their mantle, and that it compresses water and forces it out, and that the squid can also change direction by directing the flow of the water, so which way the water is going relative to its like head and its anterior end. So it's just talking a little bit about the squid and how it moves, and the like the reason we're looking at squids is because a lot of the like preliminary studies were done on the squid's giant axon. So the first question talks about in which direction would the squid move if water flows from the siphon were directed towards the head end of the organism. So previously they told us that a squid can change direction of movement by directing the flow from the siphon either forward or backward relative to its head or anterior region. So if it's pushing it towards its head end of the organism, then the squid is going to move backwards or towards its tail end. And then the opposite of that would be if the siphon were directed backwards so that it points towards the tail of the organism, then the squid would move forward. So I'm just going to write that down really quickly. All right, next we're going to learn more about squids. So it says when squids are startled or in danger, they can simultaneously contract all muscles of the mantle to forcefully jet water out of the siphon and escape rapidly. So basically, what it's doing is just increasing its pressure so that it can move from one place to another faster. And that makes sense when it's startled or in danger, right? Because you want to get away from that place as soon as possible. So we're assuming that the mantle of the squid is 30 centimeters in length, and the distance from the brain to the mantle opening is another 8 centimeter. So for all muscles of the mantle to contract simultaneously, a nerve signal sent from the brain must reach all parts of the mantle. So basically it's saying that in order for simultaneous contraction to happen, it needs to get simultaneous signal from the brain. So on the diagram of the squid above, we're going to be drawing 3 neurons. We're going to assume that they're all going to originate from the ganglion, and then that the ganglion is stimulated by the action of a single motor neuron from the brain. So the first neuron we're going to draw is it's going to innervate the mantle, and then the second one is going to be in the mid region, and then the third one is going to be at the tail end. So a way that we can draw this, so they wanted us to start from the ganglion here, and then they wanted us to draw the first neuron, and this first one is going to be the one that's innervating the mantle. So this whole thing is the mantle, and we see that it's innervating the mantle, and it's going to be nearest to the brain. So that's why we drew it in this area. And then again, from the ganglion, we're going to draw neuron 2. And I would draw something like this, and the neuron 2 is showing that it's innervating the muscle in the mid region of the mantle, so not closest to the brain, but kind of in the middle of the mantle. And the third one is the one that's going to innervate the tail end, which is right here. It's the pointy end. So we need to draw the third neuron from the ganglion again all the way to the tail end. So this is one way to draw like the different regions within the mantle and the nervous intervention. All right, let's look at the next question. So it says in invertebrate, like as the squid, how must the nervous system design be modified to allow both muscles nearest the brain and those farthest from the brain to contract simultaneously? So as you might have learned in class, vertebrate nervous system has myelinated nerves, and one big difference between vertebrate and invertebrate is invertebrates do not have myelinated nerves. Oh, I meant to write myelinated nerves. So because they don't have myelinated nerves, their transmission is going to have to be different than those innervating the muscles of the mantle, right? Because the speed of the nerve transduction is going to be dependent only on the size of the different axons, because we don't have the myelination to help with the propagation speed. So we're going to be looking at the size. And then in the drawing, we should make the neuron 1 that we drew the shortest and the narrowest, because it's very close to the origin point, right? So we don't need it to travel much further, so it needs to be short and narrow. And then neuron 2 would kind of be in the middle, like kind of long, kind of wide. And then neuron 3, we would want it to be the longest and the greatest diameter because it's going a longer distance. So I would remember that if the nerves are not myelinated, then the speed of nerve transduction is modulated by the change in size of the axon or the neuron. And more specifically, closer would be smaller and thinner. And then farther away would be bigger and wider. All right, next we're going to be looking at some research discoveries that people have done, and we're going to be looking at the different ion concentration, intracellular and extracellular. So that's the chart that they have given us here. So it's the ion concentration of the researchers that recorded for the squid neuron. So the questions are on a different page, so I might have to like flip back and forth just so you guys can see where I'm getting the numbers. So the first question regarding that is we're going to be looking at the nurse equation. And this is the nurse equation, and it doesn't just apply to squids, it can be applied to our human neurons. So if on the exam they ask you to find the equilibrium potential, then you would use this to calculate that for any ion. You would just need to modify the Z value and then the concentrations. So this would be changed, but the 58 millivolts would stay the same. So for the first one, they want us to find it for potassium. So what is the equilibrium potential for potassium and equilibrium potential for sodium? So in order to do that, what we need to do is first write out the equation. So we have 458 MV, and then Z is what it dissociates to, or like the charge. So we know sodium has a +1, calcium has a -1. So for K, we also know that it's +1, right? So we would just write 1 here. And then what we would do is multiply by the log of ion concentration in versus ion concentration out. Or sorry, it's the other way, my bad. So out comes at the top, and then in comes at the bottom. And this is where we need to go back to the table that we were looking at and find those concentrations. So here, since we're looking at it for humans, so the question said sodium and potassium in humans, we're going to be looking at the second chart. And here we see that intracellular is 40, which is the amount in, concentration in. And then here, this is 5, the extracellular. This is concentration out. And then this is concentration in. So we're just going to plug that into that equation we had. So it would be 5/40. And if we were to calculate all this out, it would be -84 millivolts. And what this tells us is that at -54 millivolts, where potassium is at its equilibrium potential. So the equilibrium potential for potassium is -84, and that's the point where potassium is at equilibrium. And then same thing for sodium, we can keep the 58/1 part because sodium also has a +1 charge. And then we're going to do log of concentration out over concentration in. And going back to the chart, we see in is 15, out is 150. So this time the top number is going to be a lot bigger. So it would be 150, 15 at the bottom. And that's going to give us +58 millivolt. So this is the potential where sodium ions are at their equilibrium. Does anyone have any questions so far on the math or just like the concept in general? All right, I'm gonna do a similar problem, but it's going to be, so this is the one we just did. I just did it on the other page, so it's asking for the human. I did that on the other page, but now we're gonna be looking at it for the squid. So again, the same concept. So we have 58/1 times log of 20 over 400, and these values are from the chart that were given to us earlier. And if you calculate it out, it should equal to negative 75.5 millivolts. And then for the sodium, for the squid, we're going to do 58 over 1 times log, and then we're going to have 440 at the top over 50 at the bottom. And that's going to give us positive 54.8 millivolts. So I just did the same math as earlier, but just for the squid instead of the human this time. All right, and I guess you can like notice a trend, like all the potassiums tend to come in like the negative values, and then sodiums have a positive potential value. So if you're ever doing one of these questions on the exam, like a quick way to know if you're like around the area that you're supposed to be, you can just quickly check that if it's potassium that it needs to be negative and then sodium is positive. It might not always be true, but it's like a general trend. So if that's not what you get, it might be good to double check the math. All right, so next we're going to be looking at a typical neuron, and we're going to be looking at the influence that ions have. So this question is specifically asking which ion has the greatest influence on the membrane potential at rest. And we know that at rest, almost all of the sodium voltage-gated channels are going to be closed, and the potassium voltage-gated channels are also going to be closed, but some potassium channels are open, and because of that, the potassium moved down its concentration gradient and out of the axon. But like the resting potential is like rarely equal to the equilibrium potential of potassium, because it's the outward flow of potassium is like generally counterbalanced by electrical potential difference. So like in addition to that, we also sometimes have some very small amount of sodium leak channels down its concentration gradient, but it's not as much as the potassium leak channels. So the thing here to remember would be that at rest, all the voltage gated channels are closed, but then we do have some potassium channels. All right, and another thing is when we're calculating the resting or the action potential of the axon, we generally don't include the concentration difference of like calcium or chloride ions. And this is because the concentration difference are like set up by active transports across the membrane. So it's like true for all like concentration difference. So we're not concerned with the concentration difference of calcium and chloride ion because the neuron membrane is essentially like impermeable to them. Another way you can think about it is that they can only be brought in through like with the help of like transport stuff. So they can't just like diffuse through the cell membrane or like through a channel like um, sodium or potassium can. So we know that they're essentially impermeable under normal conditions, which means we don't need to worry about them. So just remember that calcium and chloride are through active transport of ions. All right, next we have similar questions to what we did last time. So, but instead of them, or like instead of getting both numbers from the chart, we're gonna get one of them from the question. So it's saying change extracellular potassium from 5 millimolar to 2 millimolar. So we would take the 2 millimolar because that's the range that they gave us, but then the 140 that we'll use at the bottom will be from the chart from the earlier pages. So the equation for the equilibrium potential would be 58 over 1 times log of 2 over 140. And then this gives us negative 107 millivolts. And what this number tells us is that it means the cell is hyperpolarized because it's really, really negative. It's negative than the resting membrane potential, which is around negative 75 millivolts. So the fact that the number we got is super negative tells us that the cell would hyperpolarize. This also means it would be harder to generate an action potential because you're super negative, that it's like you have a longer way to travel before you get to the threshold. And then similar here, but we're going to see a different number. So here we see negative 49 millivolts, and we know this is above the threshold for action potential. So the normal potassium equilibrium is negative 90. Now we got negative 49. So changing the external potassium concentration with 20, which is what the question told us, would most likely change the equilibrium enough that it's above the threshold. Yeah, but if it keeps going like this, then all the neurons in your body will continue firing and it would result in death pretty much because you're just overworking it too much. All right, any questions so far? All right. So next we're going to be looking at how the neurons function to actually transmit the information. So we've just been looking at the concentration of the ion so far, but now we're going to look at how that helps generate an action potential. So these are some words to be familiar with and structures when you're reviewing. So dendrite, axon, cell body, just parts of the neuron, and then the most important ions and the types of ion gates that we're going to be looking at and what it actually does to the action potential curve. So the first question is asking us, how is action potential difference across the cell membrane generated? So that is established through the sodium-potassium pump in the cell membrane, which actively pumps 3 sodium ions out and brings in 2 potassium into the cell. So this is how we establish the negative 70 millivolts number that we get. It's because of the sodium-potassium pump. So it's going to be 3Na plus out and 2 potassium in. So what this is basically going to do is it's going to make the inside of the cell membrane more negative because as you can see, you're putting more positive charge out of the cell than the positive charge you're bringing in because you're putting 3 positive charges out, but you're only bringing in 2 positive charge in. So it's going to result in um, a more negative charge inside the cell. And that's what gives us the negative 70 millivolts. If we were to like actually measure that difference, it would be negative 70 millivolts or around there. Next, what characteristics of membrane allow cells to concentrate or exclude ions? So the mechanism that allows it for this to happen is permeability. So ions like sodium and potassium cannot easily diffuse across the phospholipid bilayer. So they must either be actively transported or diffused through specific ion channels in the membrane. So the ratio of the channels, like the ratio of the sodium channel to the potassium channel, can also affect the concentration in the cells. So selective permeability is one factor. And then we have that ions must be transported. All right, next we have what is it about nerve cells that make their property different from those of other cells? So we're looking at what is special about nerve cells that actually allow for action potential as opposed to like other cells in your body. And that is because, so all cells have a potential difference across the membrane, but what makes nerve cells unique is that they have voltage gated ion channels that open and close due to that difference across the membrane. So that's what makes them unique, and that's what allows them to produce action potential. So here I would remember that nerve cells and every other cell in our body has a potential difference across their membrane, but nerve cells have the voltage gated ions, which actually allows for the action potential to occur. And then next, we're going to be looking at how is an action potential started and propagated. So this is like a very detailed process. Like you can go super detailed. You can also refer to figure 43.7 in your biological science book, especially if you have the 7th edition. Um, that might make it easier to follow if you have access to your book. But essentially, what's going to happen is that there's going to be depolarization in one local area in the neuron, and it's going to open some sodium, voltage-gated sodium channels, right? And then what that's going to do is it's going to cause more sodium to flow into the axon. And then this is just going to cause um, it to get less negative because your more positive ions are flowing in, so it's going to get less negative. And once it hits the threshold, which is around negative 55, the sodium activation gates at all sites are going to open. So before it was just a couple, it was local, but then once it started getting more and more positive, it was like, all right, we're just going to open everything. So it opens all the sites, and now sodium ions are just going to diffuse like down their concentration gradient. And during this time, the potassium gates are going to remain closed. And then when they reach the potential difference, say around like negative 30, the sodium channels are going to get inactivated, and then the potassium channels are going to start opening. And then when potassium ions move out of this region down the concentration gradient, then this is when we start going more negative. And then finally we reach negative 70 resting potential, and then the potassium channels are also stimulated to close. But they take longer, which is why we get like the refractory period. Um, Instead of writing all this out, I can try to draw it out. Maybe that'll be more easier. The book also has some great pictures. So we could keep that as the threshold potential. So negative 55 millivolts. And then here, negative 70, we're going to have resting. So we're going to have this like slow increase, right? And this is the localized part. So like only some sodium channels are opening, but then once it hits this threshold, all of them are going to open. And then it kind of reaches this part. All right, so this part, that's going to be around positive 30 millivolts. That's where the cell is like, all right, like we've hit the top, like we need to go back down. So basically what's happening here is Na plus channels open, and then Na plus inactivated. And then once that gets inactivated, we have our potassium channels opening. And then once that happens, it goes down, down, down. But then they're slow to close, right? Since they're slow to close, they can't just close right when they get to negative 70 millivolts. So they actually dip down a little bit, and this is called hyperpolarization. But then eventually they kind of start coming back to negative 70, and sometimes the sodium potassium pump that we talked about earlier kind of helps it get back to the resting state memory potential. All right, any question on this so far? Please feel free to like type in the chat if you have any questions. All right, The next question is asking about energy input. So does generating an action potential require any direct or indirect energy input? So we know like ATP isn't being used up front, so we know there's no direct energy input that is required to generate an action potential, but we do need energy indirectly, and that's kind of what we get from the sodium potassium pump, right? That uses ATP and then that establishes the concentration gradient potential. So I'm going to write no direct energy uses indirect energy. Um, and then I'm going to say the sodium potassium pumps which generate the potential difference. All right, so next we're gonna look at what happens in time and space along the axon once an action potential begins. And that is similar to what I drew here, right? So here we have some localized sodium channels opening. Once it hits threshold, all sodium channels open, it gets inactivated, potassium opens, starts depolarizing. So that's kind of what they're asking for on question 7 too. So I'm just, or not question 7, part F. So I'm going to say refer to part, was it D? Yeah, refer to part D. And also the page on the book is a great resource. Oh, also another important thing here to note would be although like the sodium ions do diffuse in all direction of the axon, the action potential is generated in only one direction. And this is why the refractory period is important because once the sodium channels get inactivated, right, like at the peak they get inactivated, which means even though like it's like there's more ions flowing out, you can't activate it and you can't have it like go in the opposite direction. So it's important that those sodium channels inactivate so that you prevent like backwards propagation because we want it to go forward. All right, any questions so far? All right, so next we're looking at what factor ultimately limits the ability of a system to respond. This is to continue to generate impulses, and this would be the sodium potassium pump. So ultimately, this like what the sodium potassium pump does is what limits the ability of a system to respond. So if that concentration isn't set up, then the system cannot respond. So that's like the limiting, not the limiting factor, but like what would limit the ability of a system to respond. This is why like it's pretty dangerous, and there's like situations when the sodium potassium pumps in the neuron membrane are like poisoned, so they become non-functional. And when that happens, the axon is still able to generate action potential like for a little bit, and then this occurs because like the number of sodium and potassium ion that moves across the membrane during the action potential is very small. But on the other hand, the concentration inside and outside of the neuron are like measured in millimolar. So like you can have the action potential go for a little bit, but essentially because they're poison, you wouldn't be able to establish the resting state membrane after you've like used up all your ions. So as a result, like many action potential can generate before you see the potential difference is reduced enough to prevent their generation. So essentially it's saying like it would just take some time. Like if that were to be blocked, the sodium potassium pump were to be blocked. All right, next, the question says if an axon is stimulated in the middle of the length, nerve signals will move out from the point of the stimulus in both directions. Normally, however, nerve signals move only in one direction along the neurons. Explain. So basically, like normally, the refractory period prevents the action potential from moving in more than in one direction, right? So like we looked at the curve, sodium ions inactivate, so it only moves in one direction. But when an axon is artificially stimulated at any point in the length, there isn't a refractory period, so the action potential can be generated in both directions. But this does not happen naturally in the body. It's only artificially under like lab conditions. Also, for the next question, we're trying to determine if an action potential generated is postsynaptic. Um, and essentially, the only thing that it depends on, like whether or not an action potential is generated in postsynaptic neuron, depends on the type of neurotransmitter. So we're seeing, is it going to be an excitatory or an inhibitory? So we're going to look at the neurotransmitter, and we can also look at um, the type, or not the type, the number or like the frequency of excitatory versus inhibitory impulse. So that shows like how often it happens and also like how close the synapses are to the axon hillock. So we're going to look at type of neurotransmitter. And number slash frequency. And then how close the synapses are to the axon hillock. All right, and then how wide the synapse is. On average, they're around 10 to 20 nanometers wide. And then the next question says, if a synapse were 2 times as wide, what effect would it have on transmission of nerve signals from one neuron to the next? So if the synapse was 2 times as wide, the time for diffusion would increase by a square because we're looking at the area, right? So we have pi r square, and then it would take longer for the organism to respond. And it doesn't mean that it's necessarily 4 times longer to respond. It would depend, like, because it's also affected on like the neurotransmitters, vessels, and other things. We can't like accurately say that it would be 4 times longer, but we would just have to know that if the synapse were 2 times wide, the diffusion would increase by a square, and that would make the organism take a longer time. And we also see that here it says diffusion distance and then time required for diffusion. So the longer the diffusion distance is, the greater it gets. So all right, and then for our last question, it says if you examine neuron transmission within an organism, you will discover that every action potential generated is stereotyped. For example, every action potential reaches the same maximum height, the same minimum height. In addition, the generation of action potential is an all or none phenomenon. So that means like once it started, you can't like once it reaches a threshold, you can't like stop it in the middle. Like it has to go all the way up and then come back down. So given that, how does the nervous system signal differ from signals difference in intensity of signals? So the intensity of the signal is generated by the number of action potential that's fired per minute. That's like given along the neuron, or the total number of neuron firing, or both. So basically they're asking, how does the nervous system signal difference in intensity? So they're saying everything about an action potential is pretty much the same, right? Same maximum, same minimum, all or none phenomenon. So how does one firing differ from another? And that's through their intensity. The intensity of signals can differ. So one neuron or in like one place can fire more rapidly than in another place or at a different time. So that's how we can distinguish like, oh, this one's being more activated, or oh, now this one's not as active as it used to be. So we would look at the intensity for that. And that tells us number of action potential fired per unit time. right, so I know I kind of went fast through that, but that was our last question. If you have any question about the one we just did or other question we did earlier, please let me know. If not, I will put the extra credit link in the chat and please fill it out to get extra credit for showing up. All right, let me know if you guys have questions or have a hard time accessing the Google Forms. All right, everyone, I'm gonna end the meeting or the live stream right now. Again, make sure to fill out the form, and I hope to see you guys next week. And also, starting next week, I'll be holding the sessions on Thursday because I know a couple of you mentioned that the Tuesday sessions conflict with your classes, so I'm planning on moving it Thursday, and you'll all get an email about that as well. So, but I just wanted to let you know that it'll be a different time starting next week. All right, bye everyone.